Welcome guys, welcome to our video where innovation meets style. Here we delve into the fascinating world of fashion design with a twist using cutting edge technology like generative adversarial networks. Join us as we explore the endless possibilities of GNS in creating stunning, one of a kind clothing design. From conceptualizing unique pattern to crafting entire collection, we are here to showcase the intersection of creating and technology in the fashion industry. Get ready to be inspired, challenged, and amazed as we embark on this journey together. Subscribe now and let's redefine fashion design one GAN generated masterpiece at a time. Using generative adversarial networks for fashion designing is an innovative approach. GNS can generate realistic image based on the input data, which could be sketches, description, or even existing garments. Designers can use GANS to explore new styles, create unique patterns, or even generate entire clothing collection. It is an exciting fusion of technology creating in the fashion industry. Introduction to Generative Adversarial Networks. GNs are powerful class of machine learning modules that have revolutionized the field of generating modeling. GNs consist of two neural networks, a generator and a discriminator, that compete against each other to create realistic synthetic data that is indistinguishable from the real data. The concept of GNs. Adversarial training. GNs use an adversarial training process where the generator tries to create realistic data to fool the discriminator, while the discriminator tries to distinguish real data from the generator's output. Generative modeling. The generator learns to produce synthetic data that closely matches the distribution of the real data, allowing GNs to generate highly realistic and diverse samples. Unsupervised learning. GNs are a form of unsupervised learning as they do not require labeled data and can learn the underlying data distribution from the training data alone. Generator and discriminator networks. Generator networks. The generator networks take a random noise vector as input and transform it into synthetic data sample that aims to be indistinguishable from the real data. Discriminator networks. The discriminator network takes a data sample, either real or generated, and outputs a probability score indicating whether the input is real or fake. Adversarial training. The generator and discriminator networks are trained simultaneously, with the generator trying to fool the discriminator and the discriminator trying to accurately identify real and generated data. The training process of GANs. Input noise. The generator takes a random noise vector as input and tries to generate synthetic data sample that look realistic. Discriminator evaluation. The discriminator network evaluates the generated sample and produces a probability score indicating whether the input is real or fake. Backpropagation. The discriminator output is used to calculate the loss, which is then backpropagated through the networks to update the generated and discriminator weights. Application of GNs. Image generation, text-to-text translation, audio generation, and video generation. Image generation. GNs can be used to generate highly realistic and diverse images such as faces, landscapes, and even artistic styles. Text-to-text image translation. GNs can be used to generate images from textual description, enabling a wide range of application in areas like visual storytelling and image captioning. Audio generation. GNs have also applied to the generation of realistic sounding audio such as music and speech, opening up a new possibility in audio synthetic and manipulation. Video generation advancement in GAN architecture have enabled the generation of high quality realistic looking videos with potential application in video editing, virtual reality and more. Challenges and limitation of GNs. Instability. GNs can be challenging to train as the adversarial training process can lead to instability and mode collapse, where the generator fails to produce diverse output. Hyperparameter tuning. Successful GN training often requires careful hyperparameter tuning, such as learning rates, batch sizes, and optimization algorithm, which can be time consuming and challenging. Evaluation metrics. Measuring the quality and diversity of GN generated samples in an active area of research, and existing evaluation metrics have limitation and may not fully capture human perception of realism. Advancement in GN's architectures. Conditional GNs. Conditional GNs allow generator to produce sample based on additional input information such as labels or text description, enabling more controlled and targeted generation. Progressive growing GNs. Progressive growing GNs start with low resolution generation and progressively increase the resolution, allowing the creation of high quality large images. Westersten GNs. Westersten GNs used a different loss function that is more stable and has better gradient properties, helping to address the instability challenges of traditional GNs. Self-attention GNs. Self-attention GNs incorporated attention mechanism to capture long-range dependency, leading to improved generation quality and diversity. Conclusion and the future direction. Generative adversarial networks have shown remarkable progress in recent years, revolutionizing the field of generative modeling and enabling a wide range of exciting applications. As the research continues, further advancement in GN architecture, training techniques, and evaluation methods are expected to unlock even more possibility in areas such as realistic image and video synthetic, natural language generation, and beyond.
Hello guys, so this is the project which we have built. Here we are generating fashion pieces from the scratch using GANs, which is Generative Adversarial Networks. Our first step is to import the dependencies and data. Here we import TensorFlow GPU, Matplotlib, the datasets, and IPy widgets. Here is the list of all the dependencies which are installed on our system. Then we bring in the TensorFlow and we import the dataset which we are going to use for our project. The second step is to visualize the data and clean and build our dataset. Here we can see this matrix of numbers. This matrix of numbers is actually a image formed which is represented in form of a vector. Here we clean our dataset and format the shape of our dataset. The shape of our dataset is 128, 28, 28 and 1. Now the third step is to build a neural network. First we import all the modeling components, which is the sequential API for the generator and the discriminator. In GANs, we have two parts. The first one is a generator and the second is a discriminator. The generator generates random images based on its training dataset, and the discriminator discriminates the images based on their use. It, it gives us only those images which are useful for our data. Here we build the generator. This is the summary of our generator model. Here we predict the image based on the generator. As you can see, this image is as you can see, this image is the output of the generator. This image does not make any sense since it is trained on one epoch. We will use a discriminator to distinguish images from the vast subset of generator. Now we build a discriminator based on our training dataset. Here we have the summary of our discriminator, and we predict from the discriminator. The output of the discriminator will be saved in our local system. After discriminating from the generated images, we have this output. You can see we can see a shoe, two t-shirts, and a suit as our output. Each time we refresh this step, we will get a new output. The quality of the image is very low because of very low number of epochs the data was trained on. As we increase the number of epochs, the quality of the generated image will also increase. So this was about our project here, where we generated fashion products from the scratch using generative AI.